In the introduction, we saw that it's possible to think of the dynamics of a game as a state graph, like the one shown here. The game is characterized by a finite number of states. There are also a finite number of players, and there's a finite number of actions for each player. At each point in time, the graph is in one of the possible states. The players choose from their possible actions, and as the players perform their chosen actions, the game changes from one state to another. In the vast majority of games, states and actions, however, are not monolithic. They can be defined in terms of more fundamental entities. In chess, for example, states can be thought of in terms of the locations of individual pieces on the chessboard. For example, the state shown on the left here can be thought of in terms of the locations of the white king, the white queen, the black king, and the black queen. Also, in the vast majority of games, the effects of individual actions are local. As actions are performed, some of these conditions become true and others become false. However, the truth values of the majority of these conditions remain the same. The ideas of state decomposition and limited influence of actions suggest a conceptualization of games in terms of individual propositions and actions rather than states, together with a representation of the effects of these actions on these propositions rather than on the entire states. The result is an alternative representation of dynamics called a propositional net. Unlike a state machine, in which the nodes represent states, in a propositional net, the nodes denote propositions and actions, together with connectives that capture their behavior, as we shall see. One of the benefits of formalizing games with propositional nets is compactness. A set of n propositions corresponds to a set of 2 to the n possible states, all the different combinations of the truth values for the n propositions. Thus, it's often possible to characterize the dynamics of games with graphs that are much smaller than the corresponding state machines. For example, a Propnet with just 3 propositions corresponds to a state machine with 8 possible states. The second benefit of propositional nets is ease of analysis. It's sometimes possible to use a Propnet to discover independence or game factors, dead states, and other features that can dramatically reduce the cost of game tree search. In the next segment, we formalize propositional nets, and in a section thereafter, we show how to describe games in this way. In the segment after that, we see how to play games using game descriptions encoded as propositional nets rather than in GDL. And we then see how to use propositional nets in restructuring games and discovering game-specific heuristics.